Hello, everybody. In the upcoming modeling unit, we'll have lots of occasion to fit different families of function to points. And we've done a little bit on this already. This is the next and last step before the modeling unit. And the purpose of this is to remind ourselves, why do we have different forms of the same equation? So you've seen different forms of quadratic, you've seen different forms of the line. And here's a quick reminder. If you were going to fit quadratic to this curve versus this curve, for this one, it would be very easy to decide that this one is going to be the vertex, and you could use vertex form. Or you could set this point to be the vertex, and you could use vertex form to make an equation that looks like that. Here, we don't know what the vertex is. We can't treat this one as the vertex. We can't treat those as the vertex. But here we have some roots. And so it would be pretty easy to use root form to set up an equation that goes through the roots. What do those look like? That's what the notes are about. So for second degree equations, you've seen this before. So vertex form, if we don't have it shifted or scaled at all, just looks like y equals x squared, because that corresponds to a vertex here. You might have seen it in a scaled, shifted version. I'm going to use just arbitrary letters for the scale factors. So x minus b squared plus c. And so that's a version where you have shifted it right by b, up by c. So the vertex is now at b comma c, and then a is the scale factor. Okay, so vertex form, there isn't really a word for third degree, fourth degree, or higher polynomials. But you can imagine taking that equation, and by analogy, that would be a form for like the most basic version of x cubed, or x to the fourth. And also you can imagine shifting and scaling. So let's do an analogous thing here. I could take my x cubed, I could shift it right by b, I could shift it up by c, and I could scale it. And in that case, the quote-unquote vertex would be here at 0, 0, shift it right and up, and now we have a cubic over here. So you can sort of imagine by analogy all of those. Let's go back and define the term polynomial. I don't know if anyone's ever defined this for you. You've maybe heard it. So an equation with x squareds in it is called a second degree polynomial. X cubed's a third degree, x to the fourth, say fourth degree. In general, here's what a polynomial means. It's an equation that sums together, or that adds, terms with coefficients that can look like anything of integer powers of x. Oops, integer. So for example, any of the things right here. We'll go more deeply into kind of thinking about polynomials as a family in and of itself later in a future unit. But for right now, polynomials are just whenever you add together a bunch of terms that have coefficients and that are integer powers of x, positive integer powers of x. Ooh. Let's write positive. Okay, so root form. What's nice about root form is it gives you the two roots, or the two x-intercepts. So in general, we could have a scale factor here, but then x minus root 1 and x minus root 2. And what that looks like graphically is you would have root 1 as the first x-intercept, root 2 is the second x-intercept. And then again, k is the scale factor. So you can imagine lots and lots of different, let's draw a couple, lots and lots of different quadratics that go through those two roots. So you could imagine, by analogy, a third degree version of this. You'd have a scale factor, but instead of 2 terms, one with each root, you would have 3 terms. So like 1, 2, 3. And in that case, you'd have something like this. Just to make sure, I'm writing here in general rather than plugging in specific numbers for k and r1 and r2 and r3. Convince your neighbor right now let's pretend that I actually, so R3 is just a number, right? It's just this root. So let's pretend I plug in R3 as the x value into this equation. What's going to happen when you evaluate it? Decide right now. Okay, hopefully what you said is, it's hard to know what the numbers are over here because we're working with parameters. We don't know what the numbers are. They're constants. So here it would be R3 minus R1. What's that? It's some number. We don't know. R3 minus R2. What's that? Some number. We don't know. R3 minus R3. So now this becomes 0 because it doesn't matter what number R3 is. Anything minus itself is 0. And then you can think out what should happen. I've got k as a number times another number times another number times 0 is 0. So it sort of doesn't matter what k and R1 and R2 are. If I plug in an x value of R3, the whole equation becomes 0, so the y value becomes 0, and that's why this makes sense. That's why R3 gives you a root. It's because if you plug R3 in for x, this term becomes 0, and the y value becomes 0, and so now you have a root. Okay, so again, one more time by analogy, you could imagine a fourth degree version of this. It's just now you would have 4 terms, R1, R2, R3, and R4. And you could draw a little picture, 1, 2, 3, 4, and clearly they don't have to be evenly spaced. And so you could have a version that looks like this, or you could have a version that looks like that, just like all the other ones. The scaling factor of k could make it vertically flip if you wanted it to. It could make it's going to stretch it vertically or squish it vertically. Okay, so we've got vertex form is really useful if you've got a point that you want to move somewhere specific, or if you know where the vertex is supposed to be. Root form is really convenient if you have some roots. Standard form, let's do standard form. So this is ax squared plus bx plus c. And here, the a and the b and the c don't tell you anything in particular about the shape of the graph. Well, I guess except for one of them. Which one of these tells you something at all about what the graph looks like? And I hope the answer was C. So you know that C tells you the y-intercept. But A and B don't consistently correspond to any like noticeable visual features of the graph. I mean, again, I guess A sort of does. Like if A is negative, you know the parabola is upside down. But it's not like root form here, where R1 and R2 are the two roots, or vertex form, where B and C give you the x and y coordinates of where the vertex ends up. So that's standard form. Standard form for the cubic, we've talked about before, is just by analogy. Instead of 3 terms where the highest power of x is 2, you've got terms where the highest power of x is 3. So ax cubed plus bx squared plus cx plus d. By analogy here, you can probably guess. If you want to stop listening for 30 seconds and fill it in yourself, go ahead. Okay. Students always want to know, like, wait a minute, standard form doesn't seem that helpful compared to these other forms. What standard form is useful for, and we'll see this later, it's not going to be that helpful for these lessons. Standard form makes it very, very easy to compare two quadratics, for example, because you can compare them coefficient by coefficient. You can say, do they have the same number of x squareds? Do they have the same number of x's? Do they have the same constant? So it facilitates comparison between different functions. All right, so in just a second, you're going to have a challenge, and the challenge is going to be, given different scenarios, choose a form that's helpful. You might need to introduce even more transformations, and then it's the usual exercise. Plug in what you know, solve for what you don't know. But before we do that, let's just look at the most basic scenario where each of these three things is useful. So vertex form. Let's pretend I'm trying to put something through some arbitrary point over here, like 1, or like, let's make this like 5, 7. So for a quadratic, I could just immediately say x minus 5 squared plus 7, and that would give me a quadratic like this. Or I could do a cubic. X minus 5 cubed plus 7 would give me, I don't have lots of colors here, but let's do it in pencil. Sorry, this would look like this. So there's the cubic. And if you had one other point you wanted it to go through, for example, like let's put a point down here that was 4, 1. What you could do is you could introduce a scale factor, and you could plug in and solve for k. So vertex form is helpful if you actually literally have a vertex, or if you just have one particularly salient point that you want your curve to be centered at in some sense. And so you can kind of shift it over there to center it, and then introduce a scale factor to force it through other points. All right, so that's vertex given. What about roots given? Let's think about that. So let's pretend I've got, let's make it 3, 0, and 6, 0. So again, this would be really easy to do given root form, because we know that just x minus 3, x minus 6, that's going to put a quadratic curve through my 2 points. Think for a second. The curve that I've drawn couldn't possibly be this curve. Why not? This one's upside down, so I would have to have some negative scale factor here. So I could just make this negative, or I could make it negative 5, or negative 8, or negative pi, or negative 1 over root 7. Could you put a cubic through these points? You absolutely could. X minus 3, x minus 6, but wait a minute. If I multiply this out, the largest degree for my x is going to be x squared. So I need a third x. What could the third x be? It could be literally anything. It's going to give me the third root, which isn't pictured here. So if I wanted to make the third root at 0, I could do x minus 0, which is a little bit silly. Let's just write x by itself. And so then I'd have a curve that takes me through 0 and this and that. Or you could have it be like x minus 100, in which case I'm going through this point, and a point way out here at 100. You could add scale factors at the front. You could do whatever you want. But the point is, these are giving me roots. And then if all you have to do is fit those 2 points, you know, the other points can be whatever you want. And so feel free to fill in the rest of your equation kind of with whatever makes sense or whatever works. Okay, nothing helpful given. Well, yes. So what happens if I just have like 3 arbitrary points here? Like let's say this is 1, 2, and then this is 2, 7, and then this is 9, 6. Okay, well, I can't make any of these the vertex because to be a vertex, it's you got to have this nice kind of symmetric shape around the vertex, and I don't see anything like that here. And there are no roots given, and let's pretend I want a quadratic. So what could I do? Tell your neighbors. We did this like way back in week 2, I think. What's a thing that you could do if you want to fit a quadratic through those 3 points? That's right. You could set up a system. So we could say, like, and this is one thing that will always work. You can use standard form. So we can say y equals ax squared plus bx plus c, and we can plug in the xy coordinates we know. So if we plug in 1, 2, 2, 7, 9, 6, that'll give us 3 equations, which we'll write out, and we're not going to solve, but let's just remember how to do it. So the y values are 2, 7, and 6. If I plug in x equals 1, that'll give us a plus b plus c. If I plug in x equals 2, that'll give us a times 2 squared is 4, so 4a. And then b times 2 is 2b, and then c. And then here 6 is going to be, let's see, 6 squared is 36, so 36a's, 6b's, and c. And so then you solve the system. Cool. I think that you have the basic scenarios. You're ready for the group challenge.